Hello everyone, welcome back. Today we're doing another IB Chemistry HL only video on structure 1.2, the nuclear atom, specifically topic point 1.2.3, which is that mass spectra are used to determine the relative atomic masses of elements from their isotopic composition. So a key word in this topic that we'll need to learn and understand is abundance. Now, really, when we speak of abundance, this refers to the naturally occurring percentage of isotopes in a sample. So when we look at this through the lens of mass spectrometry, this is just a method that we can use to understand the abundance of different isotopes within a sample. So mass spectrometry, let me get a diagram so it's easier to understand. Your mass spectrometer will look a little something like this. So how it works is that you will have a sample which you place over here on the left. So this sample, it will enter the tube and a heater will vaporize this sample, turning it into a gas. And then an electron beam source will fire an electron spray at the gas sample, ionizing all the atoms and molecules present in it. Then this gas passes through two charged plates, which accelerate the ions further down the tube between these two magnets over here that we see. Now, these magnets, what they do is that they create a magnetic field to deflect ions. What happens is that the lightest ions, these will deflect the most. These will bend the most, ending closer to here. Whereas heavier isotopes or molecules will end up higher up here on our detector at the end of the tube. This detector will then tell us the mass to charge ratio, M to Z ratio, of each isotope. So if we were to pass a sample of chlorine gas through this mass spectrometry, this is what the sample could look like. So here's an example of what the mass spectrum of chlorine could look like if you pass it through a mass spectrometer. So what we see is that we not only have our chlorine 35 and 37 isotopes over here on the left, but we see three other values that appear here further down the right, which are our 70, our 72, and our 74. Now, because what we passed through was a sample of chlorine, we can infer that these are diatomic chlorine molecules. So our 70, our peak at 70 here, we can infer is a diatomic molecule of chlorine that is made of two chlorine 35 atoms. Our peak at 72 would be made of one chlorine 35 and one chlorine 37. And finally, peak at 74 would just be two 37 chlorines. Finally, as we said at the beginning, mass spectrometry helps us essentially weigh atoms and molecules present in a sample of a certain element. So this is useful because then we can calculate the AR mass, the relative atomic mass of this element. And by observing the peaks that we see here on this graph, the highest ones being 70, 72, and 35, we can see that the most common forms of chlorine, diatomically bonded from 35s, a diatomic chlorine of a 35 and a 37, and simply chlorine 35. That is all for this topic 1.2.3. Thank you for watching, and I hope that this was helpful.